I'm Anton Elita, Technical Solution Consultant at Juniper Networks. We have been talking about Paragon Automation Suite and its applications in the network, from planning, orchestration, assurance, up to optimization. And today we'd like to go to a deeper dive into the last part, which is optimization in live network. Right with the first case, which is path diversity. Some customers have business requirement to provide really diverse label switched paths to avoid a single point of failure in a network. Not relying on fast reroute techniques. And those customers would typically as well request a bidirectional co-routed LSP, so that the forward and reverse paths are sticking to the same set of links and nodes. In such circumstances, it is basically required to have a central controller with a global network view, just because if you look at this diagram, an ingress PE like PE1 has no idea of LSPs which are instantiated from another ingress PE like PE2. Only a controller with global view would be able to provide true diverse LSPs which have been started from different ingress PEs. I will switch to the network view now. So this is our base example network with a few nodes, and I will show now the link labels according to the ISIS metrics. We have recreated two different tunnels. One is going from Amsterdam to Berlin, and another one is going from Brussels to Prague. So they start and end on different nodes in the network, and due to the metrics that we have in this example network, they are crossing the same middle point in Hamburg. So this is a single point of failure. In case something happens there, both LSPs will need to be rerouted or will go down for a certain period of time. So how to avoid this happening? We could, of course, do the provisioning from the controller. So we have here specific tabs here to provision diverse tunnels. But I would like as well to touch upon automatic APIs. So we have in Pathfinder northbound interface using REST. And if we were to program those LSPs automatically, we would use this interface to push the request to Pathfinder. And I will now show such a REST client. I will first need to authenticate myself with Pathfinder. I will get a token as a reply from Pathfinder, and I could use this token in my programmatic APIs sent to Pathfinder. A REST call, and this content is formatted in JSON, and the content says which LSPs to create, their name, configuration method is PSAP, and we have endnodes, and we have properties for each LSP. Important are, of course, diversity level, diversity group, and that we want to create a co-routed pair ID. And the same goes for the other pair of LSPs that we are going to signal. So now I'm really triggering the send button, and I already received a reply from Pathfinder in the bottom part of the screen, mirroring basically my request and with some few attributes added like admin status and some others. So now it is safe to switch back to the network view, which suggests that we have new network events. I will refresh the LSP table to show the recently added LSPs. And these are selected now. So Brussels to Prague, and it's reverse direction from Prague to Brussels are taking exactly same links and nodes throughout the network. And same happens to the second pair of bidirectional co-routed LSPs between Amsterdam and Berlin. But if I select all four of them, this will show me that they are indeed truly diverse to each other, not crossing any single point of failure in this network. So with this, we show that using a controller with a global network view allows establishing, maintaining path diversity, even if you have a requirement to have bidirectional co-routed LSPs.
I just want to confirm that this system is also able to take into account things like shared risk link groups and coloring that can be done that can label basically underlying physical shared infrastructure as opposed to the logical one.
Yes, really great comments. So we indeed have possibility to take into consideration from the large site where we have multiple nodes and all the way down through a single link and shared risk link groups, including nodes and links.
Let's say that your network is significantly larger than this, and you need to have an explicit ERO that transits the entire network that exceeds the maximum label depth of the hardware. Does this platform support things like a binding SID to create a longer ERO than, let's say, whatever 12 or whatever the maximum segment depth or maximum label depth is?
Yes, so this is indeed a question for many service providers where the number of hops might exceed the hardware possibilities of ingress nodes. For this, we have foreseen a few solutions. One of them would be using label compression. So Pathfinder is able to create LSPs consisting of as much as a single label if you don't want to stick with specific nodes, but with your requirement, if your requirement is to go through a certain segments in the network, then indeed we can leverage binding SIDs. This is supported in Pathfinder to create smaller label stacks so that the transit node is uncompressing this binding SID and sending it over the next list of segments.
All right, so essentially, stitching two LSPs together, but they look like one, is really kind of the high-level explanation of what I've asked for. The other question I have is for LSP failover, do you have a support for running SBFD inside the LSPs? And does this support that signaling?
Yes, so we support a seamless BFD for every provisioned LSP. And this support has been as well proven at the latest EANTC meeting we had in February this year with other vendors as well.
And this is kind of relating around recent events. One of the things in the last couple of years is we saw the rise of bandwidth and the saturation of bandwidth with the pandemic. One of the things I noticed, since you have Europe up here specifically, is that the backbone infrastructures of Europe and the United States are very different. The United States depends on a lot of caching points that are very close to the provider edges. In Europe, there's a lot of PNIs, and it's largely dependent more on bandwidth than PNIs than caching. When you get into a more complex topology and scenario, how does that scale as far as being able to monitor and react? I know that in the beginning of the pandemic, we saw a lot of PNIs saturated as we were going across Eastern Europe, Central Europe, into Western Europe, and packet loss and things like that. If I'm managing this, if I'm a tier one transit provider, how would I use this to scale to be able to manage reacting to those kinds of challenges on a large scale?
So we have automated congestion avoidance in the network, which will be presented in a few minutes by my colleague Julian.
Okay.
So I'm switching to the next use case we are going to show today, and which is low latency routing. Here, the business requirement is to provide the lowest latency, or maybe even guaranteed lowest latency for critical services, with even including some service level agreements. Modern networks have really a mixed speed links which are participating in such networks, varying probably from 10 to 400 gig with all possible speed variations. So multiple service providers would base their metrics not on the delay, but they would use, for example, bandwidth as a reference for the metrics. Then it is not optimal for this business requirement, because the higher bandwidth path is not always the lowest delay. So how to solve this premium requirement without rebuilding the whole network metric system? So we have here a solution comprising multiple components. So first, we need to measure the latency on each network segment. This is obvious, and then we need to distribute this information to the controller and let the controller find the lowest delay path, having the sum of all of the delays on every participating network segment. But on top of this, we want to make sure that we understand that our customers are happy using the network, and how to measure this user experience. This is the big question, and we have an answer to this with simulating customer traffic over service providers network, so that we really see the experience that a normal user would have. I'm switching back to the network view, and I will change the link labels to show the measured delay. So we have here on multiple links dynamic delay measurement, like on the selected link, Amsterdam to Frankfurt. Some other links might have static value for the delay measurement. I would like to focus today on this cross-link, just because we have an impairment tool which would make this latency look much worse. But before I impair it, I would like to review a few tunnels, a few LSPs, which are crossing this link. For example, one of them, starting with the name LL for low latency, I have selected it now, and it goes from Amsterdam to Brussels, but it is crossing a node in Frankfurt, just because the direct link Amsterdam to Brussels has a higher latency of 15 milliseconds compared to total latency of just a little beyond 3 milliseconds going over Frankfurt. So before I explain how this data gets into Pathfinder, I will switch to an impairment tool, and we'll start an impairment on this link. So while the impairment tool is doing its job, let me explain how we get this data. So first, the two adjacent nodes, like Amsterdam and Frankfurt, they send so-called two-way active measurement protocol, T1 PLIDE, probes across the link to each other to be able to very precisely measure the latency on the link. So it is measured in microseconds. And then this information is being propagated to the IGP, like ISIS or OSPF. And from there, for each network domain, we export this data along with other traffic information. We export it to a central controller like Pathfinder. And then we are able to figure out what is the lowest delay way from Pathfinder, and all what remains is to use a PCAP protocol to signal an LSP or change a path of an existing LSP. If you looked at the screen while I was talking, you probably already noticed that this crosslink already has some average delay increased from the value of sub 1 millisecond to 35 or or something milliseconds in average for the last period of time of measurement. So how do we know that this increase in measurement does introduce any problem to our customers? For this, we use Paragon Active Assurance to inject synthetic probes which are mimicking customer traffic. For here I have a set of low latency probes which are using the customer VPNs all around the network. And you probably already see that the green bar, which is showing the quality of our service for the last 15 minutes, this is the selected interval, has turned from green to first red and then to black color. Let me explain what these colors mean. So this is a drill down view of the same active probe. We had previously a value of delay, which is according to the SLA with this customer. And then after introducing impairment, the delay jumped up to 50 milliseconds, which is breaching the contract. And then this value is considered to be equal to an outage because it is way higher than we promised. But you probably already noticed that after some time, the delay went down back to a couple of milliseconds. So let us see what happened and why the delay turned back to normal. So I'm switching back to our network view. So we already saw that Pathfinder has received the updated delay information from the network, and it reflected it even in the user interface. But what happened in the background? Pathfinder has, for this demo, aggressive LSP optimization timer. This timer reviews the delays in the network and looks for delay-sensitive LSPs and can automatically, without human intervention, reroute them to a new path. And this is exactly what happened to our example LSP that we saw a bit earlier. Instead of going Amsterdam-Frankfurt to Brussels, it now takes the direct path from Amsterdam to Brussels, just because the latency on that link is 15 milliseconds, which is way lower compared to the sum of latencies on the path via Frankfurt. And to be sure that we are looking at the same LSP, we could check the events, what happened to this LSP in the last period of time. I will select some value in the past. So this is exactly what we saw when we started our demo. And I can visually compare the LSP path as of now. So I have selected the latest LSP update, and we clearly see that the change was exactly as we noticed earlier. So with this, we have reviewed a very demanded use case for low delay service placement, continuous measurement of customer experience, as well as automated LSP optimization in a changing network environment, gives an operator very powerful tool to provide best-in-class service for their customers.
So how do you account for failures in the MPLS data plane? So something it's really common on any kind of equipment is you'll have a route that gets pushed into the MPLS forwarding database, and you've got an LSP, but the ASIC and the table are out of sync and you don't actually forward. So you're looking at this, obviously you have an LSP, you think your LSP is good, you think that you're going to move traffic to that LSP, but it doesn't actually work because of a bug and the ASIC's out of sync with the forwarding table. How would you handle a condition like that with the controller? Is that something that is part of the monitoring?
Yes. So this is very tough use case to find the culprit for it, and for this we could address with two approaches, or basically a combination of two things together. One would be, as shown previously, the active assurance probes, which in timely manner can see that the traffic is being black-holed, and it can trigger additional automated checks on Paragon Insights. So Paragon Insights might start, preparing for the network operator, which will troubleshoot it afterwards, a set of tests, like, for example, trace routes, collecting interface information right at the moment where it was triggered. This is what regards to active monitoring. But we have as well with Insights our passive monitoring, which should be run then continuously, and which would react on, for example, increased counters of traffic drops on the forwarding plane, just because the equipment usually is able to, to account for the packets dropped for no reason, like, for example, no route to the destination. And then if we have this mismatch in programming of the data plane and in the state of the routing tables, then we would probably push some data increasingly towards a black hole destination, and we will see a high increase of such counters in our monitoring tools. So there are really many counters we could monitor with this, and this is how we can tackle this situation.
If for any reason, then there will be a change triggered by the controller, and given the telemetry insights and all the mapping of the information, the controller realizes or notices that there is a detrimental effect of that change. Is the controller going to roll it back? Do you need a user confirmation or administrator confirmation for that, for instance?
So this is truly configurable, of course. So we understand that closed loop automation is the way to the future, but we cannot take it right from day one and set to boil the ocean with everything fully automated. So the trust will be gained, step by step. So today, most operators would probably trust Pathfinder to do the rerouting as shown in this demo. For a fully automated set of actions like changing configurations, maybe rolling back and doing artificial intelligence, we need time to to gain this trust. But we are on a good way here. So for this, we have already some artificial intelligence bits included in our Paragon Insights, which would help us to get there.
So we hope that our showcase did provided some light on what we can achieve today with a proven cloud-native automation stack. So if you want to continue investigating those technology, you have two options, two suggestions. One, we have an array that actually goes through the benefits of implementing such technology and that quantify those benefits. Or you can simply ask for a pilot. That's all that was shown today is proven technology. And that's technology that has been deployed by service providers around the world. So we'd like as well to thank our delegates with all their most relevant questions. And we hope to hear from you and soon. Thank you.